This is GATE 2013 question number 5, which states that across a first order phase transition, the free energy is. So this is the free energy which we generally term as the Gibbs free energy. That is, first option is that is it proportional to temperature? Is it a discontinuous function of temperature, or is it a continuous function of temperature but its first derivative is discontinuous, such that the first derivative with respect to temperature is continuous? So these are the four options which are given. We need to understand that what happens in the first order phase transition to the Gibbs free energy or the free energy. So let's come to the solution. So suppose this is the PV diagram where V is the specific volume. This V is nothing but the specific volume, and P is the pressure. This is the pressure. So this is the pressure versus specific volume curve. And we know that let us consider for liquid vapor, or for in case of a water, at some temperature T, this is the phase line which we have. This is generally the vapor phase having higher specific volume. This is the liquid phase having lower specific volume, and this is the region of equilibrium. This particular constant line is the region of the equilibrium where the pressure remains almost similar. So or it is a constant pressure which we call as the saturation vapor pressure. So this is the liquid vapor phase transition, and we call this as a first order phase transition. So what happens in that? So let us consider that GL and GV are the specific Gibbs free energy of liquid and vapor respectively. Let ML and MV be the masses of the liquid and vapor. So G1 for some phase 1, suppose, so G1 is nothing but ML into GL plus MV into GV. Now suppose some liquid is, this is some initial Gibbs free energy which we have. Suppose now some liquid is reversibly converted into vapor at some temperature and pressure. So now some of the liquid is being converted into vapor, and it's a reversible process, suppose. So when the liquid, suppose dml portion of the liquid from the ml actual, originally it is having ml amount of liquid. So from this ml mass, dml is lost and dmv is gained. So can we write the G2 as ml minus dml into GL plus mv plus dmv into gv? Now why I am multiplying with mass? Because this is the specific Gibbs free energy as I have defined here. So ultimately if I solve it, it comes out to be mlgl plus mv gv minus gl dml plus gv dmv. mlgl plus mv gv we have already seen, so this is G1, and let us consider the other term, this, as dg. So G2 becomes G1 plus dg. But for constant temperature and pressure, we know that dg is equal to 0. Why? Because dg is nothing but vdp minus sdt. So at constant temperature and pressure, if it is constant, then dg is equal to 0. This is known from the concept of the thermodynamic potentials. So dg is equal to 0. That means what? This particular portion has to be equal to 0. So dml is equal to dmv. Why? Because mass conservation. The amount of liquid, if it is converted into vapor, then same amount of liquid which is being lost, that should be added into the vapor. So dml should be equal to dmv, that is the mass conservation. The amount of mass lost from the liquid should be equal to the amount of mass gained by the vapor. So dml is equal to dmv. So if I just put it here, dml is equal to dmv, then we ultimately get gl is equal to gv. During the phase transition, the Gibbs free energy or the specific Gibbs free energy for the liquid for one phase is equal to the specific Gibbs free energy for the second phase, here in case of liquid and vapor. So what we conclude, specific Gibbs free energy is continuous in the phase transition. Now, so we have got this particular part. Now dg is equal to vdp minus sdt. This comes from the definition of the Gibbs free energy, G, which is nothing but U plus PV minus TS, and you have to differentiate and put the first law of thermodynamics, and ultimately you will get this particular expression where V is the specific volume, S is the specific entropy. This is all specific. That's why I have written it in small letters. So this is specific entropy. Now at constant pressure P, with the increase in T, we can see that the G decreases because there is a minus here. S is constant, dP is 0 because at constant pressure. So dG will be nearly equal to minus S dt, where S is constant, and so with increase in temperature there will be decrease in the G. That is clear. Now this is a kind of a graph which we generally see for the first order phase transition, where 1 and 2 are different phases and T is the transition point in the temperature. So now we can clearly see that there is a sharpness which is here at the transition point. See, this is one of the slope, this is another slope of the G versus T curve, and we can see that there is a change in the slope. Why there is a change in the slope? This is very clear. See that dG1 for phase 1, suppose if the change in the G, so dG1 will be V1 dP minus S1 dt, and dG2 is V2 dP minus S2 dt. For constant pressure, in one case the slope will be minus S1, and the other case the slope will be minus S2. So in this case, this is a kind of a situation where we have said that this is suppose slope S1 minus S1 and this is minus S2, where we can see that the S2 is higher. This is a stronger slope as compared to this. So what will happen to the entropy? S becomes minus delta G delta T at constant pressure. So this is what we have done. So this is the slope which we are drawing here. So there will be an increasing trend because G is decreasing with temperature. So if G decreases with temperature, this becomes a negative sign. Negative makes it a positive sign. So that's why S is increasing. S is increasing with the temperature, and there is a discontinuity which can be clearly seen because there is a sharpness over here. Whenever fx, some function, is having some sharpness or change in slope is seen, you can see that your df by dx is generally having a discontinuity. And if you further differentiate it once more, d2f by dx2, this becomes a Dirac delta function, where you can see that in certain places it tends to infinity, it diverges out. So since we have G which is having some sharpness with respect to T, its first order derivative which is representing this S, that is specific entropy, that must be discontinuous. And then this in the phase 2, as we know that S2 is greater than S1, so this becomes higher. The value of this becomes higher. So S2 is greater than S1. So hence this first order phase transition shows that this is a discontinuous. S is discontinuous, so or the first order derivative is discontinuous. So if we come back to the question again, we can clearly see that across the first order phase transition, the free energy is proportional to temperature. Well, not completely. A discontinuous function of temperature? No. It is a continuous function of temperature, but its first derivative, which is representing the specific entropy, which becomes discontinuous. This is the appropriate and the correct option, and the first derivative with respect to temperature is continuous. This is incorrect. First derivative is not continuous with temperature. The first order transition free energy is not a discontinuous function of temperature, and it is proportional to temperature is also not correct. So therefore this is the only correct option which is there, because G, as we know, dG is nothing but VdP minus SdT. So it's not only proportional to temperature, we cannot say that it is proportional to temperature. So this is the only correct option for this particular question. So the correct option is C. Thank you.